Okay, so in this video I am going to cover how to implement a digital system in VHDL. You have many examples available, but I figured it might be a better idea if I give you a step-by-step example. And in this case I'm going to cover the counting ones circuit, the one that you have in your notes of unit number 7. You can see it right here. Like if I give you this circuit and of course the state machine, how do I write the VHDL code for this circuit? Okay, so let's get started. Well, the first thing you have to understand is that we have to use, or in this case reuse, any code that we have already available. So this way we can save a lot of time. And as you can see here in this block, you have here a shift register to the right, actually a parallel access shift register, a counter, right? So those two are pretty common components. So ideally, I mean, you don't want to write the code again from scratch, because those two especially are pretty common components. So we're gonna do the following. We are gonna reuse some code that we already know, and that's the counter, right, with synchronous clear, and this is the name of the parametric code for it. And also the counter, the parallel access shift register with the synchronous clear. Even though we might not need it specifically here, okay, we still have this file, right, to use. Okay, so we're gonna use those two. Okay, why am I doing this? Why don't I design this from scratch? Well, I want to accelerate the development of this system, right? So these two blocks, among many others, of course, you can find them available in the tutorial, right? If you go to the unit number 5, you will see here counter modulo n, right, with enable and synchronous clear, or a parallel access shift register with enable and synchronous clear. These two are very popular. Okay, we also have, you might also need in some cases, a simple register with an enable. Those three, this one and these two are actually pretty common. You will find them, all the time when you have to design a digital system. So it is a good idea to use that code, because once you do it, you don't have to worry about this. I mean, you already know that this is going to work. Okay. If you start from scratch, there is always a possibility that you make a simple mistake with your code. No matter how careful you are, it is common for students to make mistakes. Okay, so we are going to do that. Okay, so in order to do that, I think what I'm going to do, I am going to have a new folder here, right, where I will copy these two files. Here, as you can see, that's the counter, and here is the parallel access shift register. Okay, of course I already wrote this code many times before, and to save time I am just going to use the test bench right away. I mean, I already have the test bench ready for it. But the focus here is not on the test bench, but rather on the design of the VHDL code. So then what next? Well, I guess I need to come up with the top file. And as you can see, the top file includes a state machine. So again, I can always, of course, from here, right, I can write my code for my state machine. But I prefer, again, in order to save a little bit of time, not too much to be fair, I'm going to use a simple example that I have in the tutorial. If you see this one right here, in the number 6, you have a 3 input arbiter. So this code, as you can see here, is just a simple state machine. So I can use that too, at least as a template for my file. So I'm going to use this arbiter on a copy, and I am going to paste it on this file. Okay, and I'm going to call, of course, I will call this count once. Okay, that's this circuit. Okay, and again, just to be clear, the circuit that I'm doing is such that it has 8 bits, right, on the input. Okay. So now we have the files that I need, and I think my job is only to edit this file such that it looks like a state machine together with 1, 2. These 2 blocks and the, I guess, this NOR gate. Okay. Okay, so let's continue. I'm going to open Vivado, and I will create a new project. In that folder, if you remember, the folder name was exam counts 1, so kind of a weird name. Let's call it just count once, okay? I'm going to use that name for my name of the project. Okay. And there you go. Of course, it's an RTL project. That's very easy. Add sources. I prefer to do that later. Constraints is the same. And now for the chip itself. Well, if you are gonna, go and program this on the FPGA, I think I can use the one on your Nexus 3. Sorry, Nexus 4 DDR. I think it's RTX 7. This is the package, and this is the speed, and I think it's the 100. Right? And there you go. Just give it a little bit, sometimes it takes a while. Okay, so now I am going to add sources. Of course, I have to add design sources, right? The files that make up my circuit. And those are supposed to be in the folder that you have, right? Count once, and you add what? 1, 2, and 3. Those 3. Let's give it a little bit, and here we go. So you have here the counter, my jump pulse is clear, the shift register, and the top file. The top file has this name, count1.vhd. It is a good idea always to have the same name. So that is my top file. Okay. So, and it is at this point where I'm going to start writing my code. Okay. So let's start. What is the first thing we gotta do? Well, we gotta figure out what are the inputs and outputs of this circuit, right? And if you remember, what are the inputs? Well, you have DA, of course, and you have S. And of course, you have, obviously, you have reset, not, and plug. Of course, those are implied. You also have the output C, the count itself, and the down output. Now remember, N is 8, right? So this is 8 bits. M is actually 4 bits, right? So keep that in mind. So that's what we have. So then the first thing we're going to do is to just complete the I/O, right? Remember, the whatever is in the entity, that's what we call the I/O, the inputs and outputs, right? You have clock and reset; those are obvious, right? You have S also, which is of type VHDL logic. What else do you have? The input DA, remember, 8 bits, right? So that's a vector, right? 7 down to 0. What else do we have? The output C, remember, that's also a vector of 4 bits, right? And then you also have the output down, which is only 1 bit. There you go. Okay, so we have at least that part completed. Okay, so what's next? I mean, there are many ways you can go about this, but I would say, to me, it is important that we try to use the parallel access shift register and the counter, which is parametric code. So let's do that. Okay. Remember what was the procedure? Well, you have to click here, right, and you have to copy the entity, right? That's all you have to do. Remember, these two files, the counter and the shift register, you are not supposed to modify them at all. Okay, so that's the point here. Do not modify. I will tell you how to use them properly right now. I mean, I did this already in a previous lecture, but let me do it, now again. So you copy the component right here. This is just pure syntax, right? There you go, and that's for the counter. And now for the parallel access shift register, all you have to do is to copy again the generic, the component. Right? There you go. So that's what you have. Okay. And what else do we need? We also need to usually some people prefer to write the state machine in a different file. To make it simpler here, I'm gonna just do it in this file. And if you remember, I only have 3 states. So that is my signal state. Okay. So far, that's what I have. I have my state, and I also have these blocks. What else do I need? Well, there's a lot that I need. For example, I need to declare all these signals: LA, EA, right, EC, SLRC, because I'm going to use these signals. What else? Z, and A, the output of the shift register. I also need to declare this signal. So let's do that. I mean, I think that's what I would recommend you do it. First, always declare the signals, right? For example, for the shift register, we have the following signals: EA and LA. They are type VHDL logic. These are signals to connect parallel access shift register in the top block, in this top block, right? So that's EA and LA. I also have the signal A, right? The output itself of the shift register, 8 bits, if you remember. And that's all that I need. You might say, oh, I also need this, the input. Yeah, but that's the input, so I do not need to declare the input because I have already declared the input. Okay. And what else? I also need signals to connect the counter in this top block. So that would be EC and SPRC. Okay. Somebody might say, well, what about the output of the counter? Well, in this particular case, it happens to be that the output of the counter is just the output, which I have already declared, in the I/O. So I do not need to declare that as a signal. Okay. What else? Is there something else that I'm missing? Oh, the Z. Right. That signal. Oh, that's it. Just declare it as a signal. Okay. And I think that is all you are going to need now. So what is the next what is the next step? Next step is to actually connect these blocks together. This one here, this one here, and this one here. The same machine, I'll do it last. So let's do this first, the shift register. How do we even connect that? Well, looks kind of it's a bit scary and a bit confusing, but all you have to do is to do this. I'm going to copy it here, and then I'm going to do the following. My PA shift register is clear. And I also have, of course, the port, right? Remember the port map. I have mapped the ports, right? Well, clock is easy, right? That just maps to the clock in this top block. And the same for reset. What about the input data of that shift register? The 1-bit input data, the shift in. Well, take a look at this. It's just 0. So that's easy, right? It's just 0. What else? Enable. Again, I have to look at the picture. And enable happens to be connected to EA. So that's EA. What else? I have sclear. Well, is there an sclear here? No. That means that I am not going to use sclear. But still, this block is expecting for an sclear. So I have to provide a value for an sclear. So I have to somehow, have it in a way disabled. So I have to just apply a 0 there. What else do I have? The shift load input. According to the picture, this is connected to LA. There you go. Okay. What about the data input? Oh, well, the data input is connected to DA in this case, right? You know it already. What else? And the output Q is just connected to my signal that I declare A. There you go. Now the question is, that's not enough, because this component, is what we call parametric, which means that we can always modify the size of the input data and also the direction, whether we shift to the right or to the left. So that is what we have to modify. So these are parameters. Based on these parameters, you get a different circuit. But these parameters are constants. Are constant at synthesis time. So we have to declare those parameters. So if we use port map, right, for the ports, we have to use generic map for the ports. This step is very important. Otherwise, you don't know what's going on. So n, the number of bits, right? How many bits do we have? 8. What about the direction? According to this, it is a string. It can be either left or right. Let me see if here is properly. Yeah, the direction can be left or right. Okay, so all you have to do is take a look at it. This is right, so you just have to use, in this case, right, like this. Okay? And there you go. Now you have actually set up the proper parameter. Okay. I recommend when you do this, you at the beginning when you're doing this, don't pay attention to these online errors. I mean, most likely they are mistaken. Okay? The best way to find out if there is an error is by looking into the synthesis. Okay? So that is the first thing. Okay, the shift register. So I have that ready for me. Right. What is next? I have to use my this circuit, the counter. Okay. Well, the counter we're gonna see. Let me see. It's gonna be very similar. So again, I'm gonna grab this. Right, and I will do the same, right? I have to use, I have to map the parameters as well, and also the ports, right? So what about the parameters? Well, in the parameters, there is the count. What is the count, right? Because that means that this counter counts from 0 all the way to the parameter count -1. Okay, so I have to provide a value for the count. What value is that? Well, we have to figure that out. If I have here a circuit that counts, as we know, the number of bits in this signal, the number of bits here can be from all the way from 0. Sorry, the number of ones, right? So the number of bits that are 1 can be 0, could be 1, all the way to 8, right? So what is the count then? That would be 9, right? So that's the count that I need in this particular example. Okay, so I just do here 9. Okay. What about the port map? Well, that's easy. Clock is always connected to clock. Reset. What about the enable? Well, that's easy. Enable is, as you can see here, connected to EC. What about it's clear? Here is connected to SCRC. What else do we have? Q, the count itself. Well, that one has supposedly, if this is 9, the logarithm base 2 of this would be 4, right? Remember, if the counter in this case has m bits, because it comes from 0 to 8, we have 9. So m is going to be 4. It's the number n, of course, plus 1. So it's 4 bits. So, and of course, that matches what I have here. Okay, so I have here Q is just equal to C. Sorry, connected to C. What about the output Z? Remember the output Z of a counter that becomes 1 when we reach the maximum count? Well, in this particular example, we do not need that signal. In that case, we can do this. You can just do it like this. Open, right? Which means that it is connected to nothing. Now remember, outputs, you can always do this. You can just leave the outputs floating. Inputs, you cannot do this. Like in this case, we can say that we are not using sclear, but if you are not using it, you have to provide a value for it. Okay? Outputs, you can always leave it open, or you can just omit them. Okay? And there you go. That is the circuit. Okay? So, we're almost there. What else do we need? We need also A0, but that's easy, right? A0 is just the output A, 0. We don't need to do actually anything about that. What about this 8-bit NOR gate? Actually, that's pretty easy, right? All we have to do is to just apply the NOR operation to all the bits of A. So Z is going to be what? Not A7, right? Or A6, or A5, or A4, or A3, or A2, or A1. Somebody might ask, is there a I guess a more systematic way of doing this? Yes, there is. Okay, but I guess I do not teach this in this class yet. The idea is not to make it, this more confusing than it is. But yes, absolutely, there are ways to simplify this instead of me having to write every single case. So now I have most of my signals ready. So I have the counter, I have the shift register, I have the signal Z, I have everything now that I need. So what is next would be the state machine. Okay. Notice that by using the parametric code for the shift register and for the counter, I don't have to worry about the code inside the counter. I know already that that works already. Okay? Because that code has been tested already extensively. So now we need to do the state machine. So that shouldn't be difficult because I already have somehow I have a state machine already. So what are the inputs there? S, Z, and even A0. So first I'm going to do the transitions between states. As usual, when there is a reset, we go to state 1. What happens when we are on state number 1? I'm going to delete all of this. So according to this, when we're on state 1, right? If S is 1, we move to state 2, right? That's easy. So if S is equal to 1, then we move to state 2. Otherwise, we remain on state 1. There you go. That's all. And now I have to do the case for when we are on state number 2. In number 2, I have the following. If Z is 1, I go to S3. If Z is 0, I remain in number 2. That should make matters pretty simple, right? If Z is 1, I go to state 3. Otherwise, I remain in state number 2. And there is one more, of course. There is state 3. And in state 3, it's very simple, right? If S is 1, I remain in state 3. There you go, and that's all that I need to do for this case. Okay. Now, that was relatively easy, and now we have to go on to what I think this is where a lot of students actually make a lot of mistakes, and this is pretty common, by the way, the output process. So what are the inputs here? Well, again, the state S, Z, A, 0, if you like. So now, notice something, right? This is state machine, right? The next state, sorry, the outputs, like this output here, depend on the current state and also on the value of the input signals. So what does that tell me? It is telling me that this is a milli state machine, right? Also, always remember that this output process is just a combinational circuit. It is just logic gates. There are no clocks there at all. So let's do it then. Let's start. Let me take a look. So what are the output signals here? Well, I have LA, EA, EC, S clear C, and on. I have 5 output signals. So again, what is the most important thing that you gotta do is assign what we call the default values. So let's say EC will be 0, but that's a default value. Some people make the mistake of thinking these are like initialization values. Remember, we're not doing software, this is just pure hardware. We are just setting up default values such that when the signal is not specified, when the value of a signal is not specified, it will default back to the 0. That's what we want to do. Okay, and now we complete this. So here, on the state 1, look at this. EC and S clear C are 1 directly. Well, let's do that, right? So that would be EC equal to 1, S clear C equal to 1. There you go, that's all. What else? If for some reason S becomes 1, EA and LA are 1. Oh well. If S is 1, then I say EA is equal to 1, LA is equal to 1, and then I just finish that. That's all. That was my state number 1. Okay. What about state 2? So let's take a look. In state 2, well, everything depends on Z and A0. But look at this. If Z is 0, I know already that EA becomes 1. Well, if Z is equal to 0, I know that EA becomes 1. Now, this, I guess, if you like statement here, is actually nested within Z, right? So this is a nested if state. So if A0 is 1, then EC is 1. There you go. So here I just do the following. If A0 is 1, then EC becomes 1. And that is all I have to say. Okay, and now we are on to state number 3. In number 3, well, notice, this is actually pretty easy. All I have to say is DOM is equal to 1. And there you go. Okay, that is all that you have to do. Okay, it is actually pretty straightforward, right? But of course, you have to know your theory. A single mistake can derail your entire circuit. Okay. Something that I've seen before, some students make this mistake, I think unintentionally, when they are saying if S equal to 1, sometimes they do this. If S, let me tell you something. This doesn't mean S is lower than 1. It means S is assigned to be 1. That's what it means. Therefore, this statement, right, is always true. So if you ever do this, and this kind of mistake, that means that regardless of the value of S, EA and LA will be 1, which is not what you want, of course. Now remember, this kind of statement, this is not a syntax error, right? I guess this is rather a miscoding, if you like. You're making a mistake in the coding style. Okay? So please keep that in mind. That particular mistake is actually very difficult to spot. Okay? The synthesizer will say, oh, it's okay, because this is a valid construction in VHDL after all. Okay? Okay, so please remember that. So here we go. Okay. Okay, now, like I said, usually don't pay attention to the to this online thing. Okay. One thing that is important though to remember is that this thing, because it's parametric, I have to use this kind of weird functions, right? But these functions are in a library, and if I want to make sure that this works, I have to actually use them here. And this is actually pretty easy. All I have to do is I go here and I just use this library, and that's all. That should take care of it. Okay. You would think that is the reason why it is complaining, but here we go. Oh yeah, oh well, it works. In other versions of VHDL, sorry, of Vivado, in like 2017, even when you copy this library here, you would still see a red line here. That is a bug, and I'm happy to see that in this version 2018.2 it has been fixed. Okay, so now we have everything ready to go. Okay? If we're lucky, there won't be any syntax errors or even weird warnings. Okay, so what is the next step? Well, the next step is to do synthesis, right? Remember, never just go and simulate. You have to do first synthesis and check, of course, check syntax error, those are obvious. Also check critical warnings, those are almost, essentially they are errors, essentially, and warnings. Some warnings, like I said, this part is, by the way, tricky, because some warnings are important, others are not. But like, let me just tell you here, just in case, some important warnings that will essentially make your circuit not work. There is one that is called inferred latch, which happens a lot in the, especially if you forget to declare, some default values, and you create a latch, and that's again very hard to detect. Another one that is common is signal, something like this, has no driver, which means that there is an input pin in your circuit that has no, that it's unconnected. That's very bad. Or another one is multi-driven signal. That means that essentially this is a short. Okay. Essentially what you're doing here is actually, it's like as if you were, imagine if you were hooking these two together, right? That would be a short, right? Two outputs are being hooked together. That's a short. If you were to do that, you would see this kind of error, multi-driven signal. Okay. Now, of course, I don't think any of you would do this intentionally, but remember, since you are writing a kind of large code, it is easy to unintentionally do this kind of mistake, and it won't be so obvious as this. Okay, so like I said, check for that. So that's what we're gonna do now. We're gonna run the synthesis. Let's see what we get. Okay. Let's give it a little bit. It's gonna take a while. Like I said, I already worked on this before, and of course I already have a test bench. Okay, so once we clear the synthesis, we're gonna actually run what we call behavioral simulation. Okay, so please always follow the steps. Okay, do not try to jump one step. I see many students, they just directly go to behavioral simulation. Okay. That's not how you do this. Okay, and you will actually spend more time with that. taking longer than expected. Usually it does. Let's give it a little bit. Okay, now it completed. At that point, all you have to do is you close this, and then you go to the project summary, and then you check on the warnings. Oh well, and we're lucky us. We only have one warning. It says no constraint written out. That's nothing, because all that it is saying is that there is no XDC file, which makes sense because we have not declared yet an XDC file, right, for the I/O in the actual FPGA. So that's okay. So there are no warnings. So if you have no warnings like this, I mean, your circuit is actually very good. It's was written in a proper way. Still, that doesn't mean, right, that it's done, right? I mean, let me make it clear. No warnings or no or even or errors in synthesis, right, does not mean you are finished. It just means that there is no some glaring errors, some clear errors or warnings. Your circuit might be, I guess, coding wise sound, but it is possible that you made a misconnection, right? What do I mean by a misconnection? Something like this. Let me see. Let me show you. What if, for example, for some reason, you connected LA, because by mistake, by the way, this happened. You connected LA to EA, and EA to this signal here of the shift register. This is not an error, I mean, for VHDL, for Vivado, right? Because Vivado has no idea of what you want to do. So for Vivado, if you make this connection, right, from this signal to the shift and load of the shift register, and for LA to the enable of the shift register, as far as Vivado is concerned, that's okay. Okay, so these kind of misconnections are very common, right? Very difficult to spot, and that is why you have to simulate, right? Only by simulation you will know whether the circuit works as expected. Okay, so let's be clear on this. Okay, synthesis only means that it's checking that there are no weird connections, right, or something very, very clear. Okay, that doesn't mean at all that you are finished. Okay, so now we do behavioral simulation. Well, to do that, well, you have to, of course, write your test. And of course, to save time from this, I just want to use the test bench that I already have available. So I'm going to use that test bench, of course. Something, let me see. Well, you have to be careful, of course. Test bench is okay. But I named my circuit, I named it actually count one. So that's why it's complaining. There you go. Count ones. And of course here it also has to be count ones. Okay? The test bench is actually very simple, right? All it does is just it loads some data, right? Makes S equal to 1 for a cycle, and then it just makes S0, and then it lets the circuit, work. That's pretty straightforward. Okay, so when you do this, let me do something for you so you know what I'm talking about. Let's say by mistake I do this. Okay, and then I run the simulation. Well, there is here, of course, online. So actually, in this case, it's actually going to help you, but usually it doesn't help you too much. But some other errors are not as clear as that. Okay, but in any case, you do that, and what you do now is actually you simulate. And let's see. Okay, let's see what happens. when you run simulation, the simulation errors will be listed in the tickle console. Okay. So look at this. There are, of course, there are errors, or maybe not. So in the tickle console right here, you will find some errors. But in this case, and this is, I think this is a very good example. We did not find any. The tickle console did not find any error. Let me see. It found a warning though. Not top level signals found. But that makes sense because in your test bench, of course, this block does not exist. It's actually this block. Okay, and that is why in your simulation here, all you see here is just unidentified signals. That makes sense. Okay, so we're gonna close it. I'm gonna try again. So again, the simulation errors or even warnings, right, will be listed in the tickle console. That's something that you have to be able to always take a look at, okay, to see where the mistake is in your simulation. It won't tell you everything, by the way. It will only tell you the, some very clear errors, right? Okay, so that's what we have right now. So let's try to see if we can, force an error. Let's say I use, instead of done, I use done s, because I made a mistake. And let me try to run the simulation. Okay. Let's see. Aha, now you can see an error. Many students here, when they click this and click OK, and they don't know what to do. But look at what it says here. You have to check the tickle console or output to get more information. So you go here to the tickle console and you scroll up to the first error. The first one is the one that matters. Right here. Okay. So this makes sense because that means that this signal is not declared. So that's actually more helpful than anything. There you go. So now you fixed it. And now we're gonna run it again and see now, hopefully this time we will get something useful. Okay, so here we go. This is this thing right here. Okay, here we go, the simulation. So again, notice something very important. The simulation by default, if you don't know it already, right? It will run for 1 microsecond. Okay, so keep that in mind. And you have here DA, the input, and the output. So again, you have to make it bigger to take a look at it. And even bigger than that. So you have 3, 6, and that's gonna get you 4. I think that makes sense. Let's see. Let me take a look at the binary data here. A little bit more. Oh yeah, 0, 0, 1, 1, 0, 1, 1, 0. So it's 4 ones. So therefore the output is 4. This is what I expected. Okay, but of course, usually that's not what you will find. Usually it won't work at the first time. So this is why it is very important that you are able to pull out the internal signals. For example, one thing that I want to be able to get is the state. That's very important to me. Then I guess if I want to check that this is working or not, I would say this signal also would be very helpful, right? Or even these signals too, right? So how do I do that, right? Or even Z for that matter. That might also be important, right? How do I get all these internal signals? Well, remember, your simulation is like a scope, right, of your signal. So you go to the scope tab. You go to the UUT, which is your block. Remember, in your test bench, this is UUT. That's your block itself. And here it will show you all the signals available in this block. Sorry, in this file, in the count ones file. So I guess I can just get the state, EA, LA, even A, even the output, right, of the shift register, even EC, C, and Z. There you go. I can add them to the wave printer. There you go, all of them. What else? Well, sometimes the signals that you want might not be here. They might be inside these blocks. So you have to click in each of these blocks to pull out any other internal signal that you want, okay? And then somebody asked, well, how do I run this again? Because after all, there is nothing here. Oh well. You have to restart the simulation using the tickle console, and then you run it for, I don't know, like I said, 1 microsecond is the default. I think for this I only need 500, even 300 nanoseconds. That's enough for me. I can, by the way, always keep running more. Look at that. Here we go. This is your data, right? This is your data, and this is all the signals. Look at the state, right? I'm going to put it in a different color just in case. S1, S2, S3. Here you go, S3. So you can see, for example, that the state machine is going through all the states. EA and LA, EC and SPRC, you will see how they change. And of course, you can always check whether they are okay or not. Okay, this is very, very important, by the way, a very useful tip. What else? Sometimes it does not happen here, by the way, but sometimes you might need to run for longer than that. So you just keep running, right? You can say run I don't know, 3 microseconds. That's probably a lot, by the way, for this case. And you run it, and you see, you keep running forever essentially. Okay. Let's say you have already, changed the color here. What else? Added these signals. What if you change your circuit and then you want to simulate again, but you want to, of course, keep this showing these signals? You have to save this waveform. You save it, and it will ask you whether you can add the waveform file. If you say yes, right, next time you do your simulation, the signals right here are going to come back. Okay, and that would be all. All right. So, and by the way, this in case you want these files, right, they are already posted in Moodle for you to just download the code. Okay. Anyway, thank you.